بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So today we're going to do practical introduction to logistic regression and binary classification from programming point of view. So the objective of this notebook is to introduce binary classification using logistic regression, which we have already introduced during the lectures. And we will, as usual, create a synthetic data to make binary classification. So let's start by importing the different libraries and just creating the binary data. You can run the notebook with me. So we will generate binary data, and so this binary data will represent two features, X and Y, and one outcome. Okay, it's very simple example that we create here. Look, so this array represents the input feature, X and Y, and this is the output, either 0 and 1. So we will have, it's like we will have collection of points in two-dimensional space, and we want to make separation of these two-dimensional points based on their colors or based on their class. 0 maybe could be one color and 1 a different color, just for visual illustration, as we will see over here in this graph. Okay, so this is our problem now. Every point represents an XY coordinate. This is why we have two features. It's a visual representation. You can think about, you have two features, so you have two-dimensional space, input, and one feature in the output, which is the class 0 and 1. And here, visually, we represent the class 0 as blue color, and the class 1 as the orange color. So what we want to do now, given a certain vector of two-dimensional space, with two features, what will be the outcome? So we have a lot of data now. And visually we can observe that there is a pattern. صح ولا لا؟ يعني the orange points are almost toward the upper right, and the blue points are toward the bottom left. So there is a clear boundary between the two classes. And we want to use logistic regression, because logistic regression, it will provide us two outputs as a probability, okay, 0 or 1. So we can classify these points. So basically this is our data set. It contains points XY coordinate with a label. And let me show you feature number 1, which is the X coordinate. Let me visualize it. So this is the first, this is the array of feature number 1, all the X values. These are all the X values, and they can show all the Y. I can show all the Y values as well. So every feature will have a distribution by itself. Okay, this is why we can visualize the distribution of data. This is feature 1, and this is feature 2. And of course, so feature 1 distribution by class, and feature 2 distribution by class also. Yes?
Each feature has its own, why each feature has two lines?
Because there are,
XY.
yes, it has XY coordinate. This is for class number 1, because some X, they belong to the class number 1, and some others, they belong to the class number 2. Okay, so these are all X values, the distribution of X values that belongs to class 0, and this is the distribution of X values that belongs to the class 1. Okay, because every point, now for example, this point, it has an X that belongs to the orange class, and this one, this X belongs to the other class. And look now, for example, here it's basically the same X, and they have two different classes. Why? Because the class is not identified by one feature, it's identified by two features, X and Y. Okay, so if you want to make logistic regression based on one feature, you will not be able to have correct classifier, because the same X could be classified into different ways. And this is why we have overlap, some overlap. Okay, so now we have understood our data. Look, we're going to build a predictive model, but still we go through an exploratory data analysis. We need to understand our data. We need to visualize it, okay, before going into that level. So this is an interpretation the scatter plot shows clear diagonal separation between classes 0 and 1. So we can see that there is a boundary line that will separate between both. Points slightly overlap because there is 10% noise in the generation of the data. Okay, there is in the generate function, there is a noise. Okay, because there is a randomness here. There is a randomness of the noise. Okay. That's it. Now the next step, data visualization. Let me complete. So feature distribution, both features shows Gaussian distribution. It's the normal distribution. Class 0 centered around minus 0.5 here, and the class 1 is centered around 0.5. So now we need to prepare our data for training. And as we did before, we need to split the data into a training data set and a testing data set. What is the purpose here of this split in train and test? Yes?
Train the model and then have enough data to evaluate the accuracy of the predicted model.
Have enough data of what? It's not very clear what you're saying.
Some data for training, validation, testing.
Yeah, I didn't learn anything here.
Maybe to generalize.
Why we use the testing data?
Testing the model.
Of course, we test the model, but what does it represent? Unseen data. This is what I want to hear. It's data not used in the training. Okay, because we want to emulate. If I train my model, take it to the production or to the deployment, will it behave correctly? So I will need to compare metrics of the training with the metrics of the testing. That has to be clear. Okay, of course we'll use it for testing, but this data will not be used in the training. This is the most important information about the testing data. Okay, so now we will make a split. We have 1,000 sample. We will take 800, which it's sufficient. It's 80% of the data, and 20%, 200 sample is also sufficient to train. You can change to 90%, 10%. That's also another possible distribution, and you can choose using the test size. So you present the percentage of the test size, which is here 20%. Okay.
How do we know what's the best?
It's a hyperparameter. You know, when we train models, we have what we call hyperparameters. We don't know in advance which one is the best. Sometimes we can have like an initial assessment based on previous experience of others. For example, the learning rate must be small. Could be, for example, 0.01 or 0.005. But usually you need to start, make initial observation, and then based on the observation, you can increase or decrease these hyperparameters. So in machine learning and deep learning projects, we usually start with what we call quick and dirty model. What does it mean, quick and dirty? Something quick to make an initial observation about the behavior. For example, the gradient descent is very slow. So maybe my learning parameter is very small. I need to increase it a little bit. Or I find a lot of fluctuation. No, there is something wrong. Maybe I didn't do normalization. Maybe the learning rate is very high. So you need to make small, don't try to spend a lot of time making something that you think sophisticated and then it's going to fail. Start with something small to make observations, and based on this you can make iterations to improve the training process. Okay? So you can later on train with 90%, 20%. Now there is always an advantage with increasing, decreasing the training percentage. When you increase the training percentage, so you'll have more data to train. So your model will have different type of data to learn from it. So this helps maybe to make generalization, but also it can lead to overfitting. So there is always a balance. Also, if you decrease the number of testing data, you will not have enough sample to tell whether my model is general for unseen data. So the selection of this model has to be done carefully. Now, usually we do the 80-20%. If I have a huge amount of data, I can make 90%, 10%. For example, if I have 10,000 data set size, I can make 90% in training and 10%, because 10% is already 1,000 sample.
Yeah.
Okay? 1,000 sample is sufficient. Even 5% is sufficient. 500 in the testing data could be sufficient as well. But I cannot do here, for example, 5% for testing, because 5% will be only 50 sample. It's not representative enough.
What if we have like 100 samples? Can we do like 95 to 5?
100 sample is not even sufficient maybe for training. And it depends on the complexity of the model. Now, this is a binary classification on 2 features, so it doesn't require too much data. I mean, even now in traditional machine learning and deep learning, I mean, 1,000 sample is not sufficient to to teach complex models. Okay, it depends on the complexity of the model, but this is a simple model.
Why don't you use cross validation faults, validated faults?
No, today my focus is more on classification report and the evaluation. But of course, if you want to make it better, you are true. We need to make cross validation. We did one notebook about cross validation. Yeah, we can combine both. But today I would like to introduce more how we evaluate a classification model. We still didn't do the training, so let's move forward. Okay, so for logistic regression, it has several parameters. Now, usually we use this, it's the default parameter. But what are the default parameters? I presented all the parameters here. So it has two parameters for what we call regularization. Okay, so regularization, I didn't talk about this in the previous lectures, but usually when we define a loss function, what do we like to do? We would like to optimize the loss function with respect to the training data, صح ولا لا? But in some of the cases, we can have overfitting. It means the loss function is over-optimized with respect to the loss. So one of the ways we measure. So one of the ways is we can add a penalty to the loss, which is an additional value. So this additional value, we will not optimize the loss with respect to the training, but with some additional penalty so that the loss doesn't overfit to the training data. هو عبارة على an additional factor نزيده. When you make the derivative, it will not be the derivative with respect to the loss, but be the loss plus a penalty with an extra value. فالloss will not be over optimized for the training. فهذه regularization تسمح أنه the model will be more general. This is just in brief. Okay? So there are different type of regularization مثل L1 ولا L2 depending on their expression. And this is the C factor because regularization has a factor lambda اللي يعطينا الويت. هل نحب نبعد النموذج أكثر شيء على اللوس ولا نخليه قريب. So it's another hyperparameter. And maximum number of iterations, how many steps you want to train your model, your initial seed, so you can change the seed in order to explore other space, and tolerance for stopping criteria. This is like the tolerable error. If you reach a loss with 0.0001, then you can stop the training. Okay. So this is the logistic regression that we defined with these parameters, and then we can use dot fit. If you want to train more, you can change this parameter. So you can train it for longer time. Okay? And now, after doing that, so we have a model, and we want to test this model. We want to evaluate it. We can make simple predictions on, look, you can take one value from the test sample. Now, this is a value from the test sample, X test. Okay, so this is my input from the X test, and this is the ground truth. So I can get the ground truth by doing Y test or Y test. So in principle, this input must give me the value of 1 as a classification. We can take now, this is the true value. This is the true value, and you make prediction. So let me take the sample and apply the model that I trained here. Okay, so I can do, let me take it step by step. This is my model, and then I will make dot predict single sample. So this is the prediction. What do we have here? We have a misclassification. Okay, the two values are different. So here we have one misclassification. Now the question, how many misclassification? No, just a moment. Let me bring this one. Maybe it's not the same. Now it's not a misclassification because this was from single sample. Maybe it's a different value. Now I have a correct classification. So now my question, how many misclassification I will have? ذكروا أمس we talked about true positive, true negative, the confusion matrix. So this will give me the clear picture about the performance of my model. Now let's run this cell. Okay, we have a sample feature. This is the ground truth. This is the predicted class, and these are the probabilities. Look, now in order to get this value, the logistic regression predictive model will return a probability which can be between 0 and 1. It will not return 0 and 1. So here the probability of it is class 1 is 86%, and here the probability of its class 0 is 13%. Now the model decides that this class is likely to be 1. Of course, here we use the default threshold, which is 0.5. Okay. Now we can also use the threshold testing. Now what if I change the threshold, not 0.5? We can do that. So we can run the test with different thresholds for different values, and then let's see what happens. Okay, if I run the threshold 0.3, I will have a correct classification. Now in this case, I have all of them correct classification. Let me put 0.1 as a boundary. ها؟ المفروض يطلع غلط. نعم. Default decision. It's true. It's strange. Let me try it again. خلينا نجيب probabilities. It's strange.
So it was supposed to be false.
Yes, in principle. And I want to bring the probabilities to see these probabilities over here. Okay, let me try it for another one. So I will take, yeah, no, this doesn't work. Okay, I choose another value. Let me change the threshold to 0.3. Maybe it works. False. Okay, so you can see that the threshold will play a role in the classification of a model. Questions? Okay. Okay, so here it will show the class probabilities, and based on this, okay, these are the class probabilities. Probability of the class 0.46. Look, this is because it's very close to 0.5. Okay. You can also do batch prediction. So what does it mean, batch prediction? You don't need to predict value by value. You can predict all the vector. Look, don't predict all the X test. So this will return what? It will return. These are the probabilities that will be generated for the true case. Okay, so this is likely 1, could be 0, 0, 0, and so on. So it's probabilities. It will predict probabilities. Yeah, this one is predict probabilities, and this one binary, it will return 0 and 1. Look, let me print, because they are different. They are different. Let me print this one first. Look, the predict will give you the class. Predict probability will give you the required probability. Okay, the probabilities. Okay, look now, because we used 0.5, so this one was 1, 0, 0, 0, 0, and so on. Now the question, how many misclassification? How can I evaluate this? And this is why we use a classification report breakdown, as we introduced yesterday. So to do that is pretty much simple. We can import classification report. So classification report is imported from scikit-learn metrics. Okay, let me bring it here now. So we import classification report, and here we will find all the information about our data. Now, how can we interpret these results? What do you observe? Now, this is important. The result interpretation. So the accuracy of our model is 93%. This is the average. Okay? It's the true positive, true negative divided by the whole data. Yani, over 100 sample, 93 are correct and 7 are wrong. Okay, and then you decide whether this error is acceptable or not acceptable. So for class 0, we can find, okay, this is the interpretation of the previous example I've done, because the split has changed and the model has changed. Okay, this is how we interpret it usually. We have class 0, it will give us how many samples now in each class. We have 95%, 95 of the 200 were class 0. Now in our case we have 102 out of class 0. Because when you do the split, you can have random values of 0 and 1. So we analyze the precision, we analyze the recall. What is the difference between precision and recall?
Precision accuracy حق class 1 والrecall هو how much it remembers.
Yes, recall how much it remembers the true positive. Okay, which is the true positive divided by true positive plus false negative, if you remember. Okay.
I think that could be like an interview question.
Yeah, they are tricky, the difference, but these things you need to memorize them. Okay, a data scientist must understand these metrics quite well.
يعني طب كان الريكول 0% يعني فرصة إنه يعطيني random value كل مرة صح؟
Yeah, now, the interpretation, it will differ from one discipline now because we're working on an abstract example. لكن مثلا لو اتخذها في المجال الطبي في عندها معنى مثلا. Okay, because if you مثلا you make a binary classification whether an X-ray is a cancer or not a cancer. And then the positive case is cancer. Okay, and then it can be an issue if the recall is bad. Because if it cannot identify cancer as a cancer, cannot recall it, it could be an issue. So maybe it's less critical that I misclassify a negative case rather than a positive case. لو شخص عنده مثلا عافاكم الله سرطان نقول ما عندوش سرطان، هذه إشكال. لكن هو ما عندوش ونقول عنده. It's not a big deal لأنه في الأخير I will do additional diagnosis. So it depends on the context, the interpretation. Okay, so usually the positive cases could be more critical. This is why we focus on them. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So yesterday we have introduced the classification report, okay, which shows how we can assess the performance of a classification model, and we have defined the metrics, which are the true negative, the true positive, the false negative, and the false positive. Okay, and based on this, we defined several metrics, including the accuracy of the model, which is like the general average of the performance, and then we also defined the precision, the recall, the F1 score, which is like an average combination of precision and recall. But we have also discussed that this classification report is basically related to a threshold value, which is by default equal to 0.5. And you made some observations that changing the threshold value will change these metrics. We change the true positives and the true negatives because the threshold value will decide whether to assign a certain probability to 0 or to 1. So the question now, how can we evaluate the average performance or the global performance of the model for all possible threshold values? Okay, so the threshold value, as you already mentioned, okay, if you take a decision boundary or decision threshold 0.5, so in this case we can decide that this one will be assigned to yes. But if I choose the decision threshold to 0.6, so in this case this one will also be assigned to 0. So how to evaluate the performance of the model regardless of the threshold? We usually do that through the metric called receiver operating characteristic curve, which is in short the ROC curve. So the ROC curve is a graphical representation, which you see here in blue, of a classification model performance for different threshold settings. So if we calculate a certain metric, which we'll introduce now, for different threshold metrics, every point will help to plot this curve. So this curve will represent a characteristic of the classification model, and then we use this curve to calculate the area under that curve, and this will represent the average performance of the model. So how do we calculate this curve? Let's take it step by step. First of all, we will calculate the true positive rate and the false positive rate. It's not the number, it's the rate of the true positive and the false positive. So the false positive will be the x-axis, and the true positive will be the y-axis. So this represents a two-dimensional plot with xy coordinate, where x is the false positive rate and y is the true positive rate. How do we calculate them? So as we can understand from the definition, we will take the true positive and we will divide by the true positive and false negative, because false negative they should be actually true positives, but they were misclassified. So this will represent the percentage of true positive. This is why we call it a percentage or a rate. Okay? And the percentage will be always between 0 and 1. And here for this metric, the false positive rate, so false positive divided by false positive plus true negatives. This is the false positive rate. We have true positive and false positive rate. And then for every threshold value, we will calculate these two metrics. For example, for a certain threshold value, look, if I take a threshold value of 0.1, I will have a high true positive rate and also another high false positive rate. If I take a threshold value of 0.9, I will have a low false positive rate and a low false negative rate. And for 0.5, I will have a high false positive rate and a low false positive, true positive rate, high true positive rate, and low false positive rate. So what is the best value here? Which one represents the best performance? هي النقطة هذه, which is almost 0.5. So 0.5 in this case is the best, because what I want to achieve? I want to achieve the highest true positive and the lowest true negative. Okay, now for example here, I still have smaller false positive, but it's not good, because I also don't have high true positive rate. Okay, now
توتال هو المفروض يوصل واحد.
which total?
إذا جمعنا البرو يعني هذا والثاني التي بي ار والبي ار مو المفروض يطلع واحد.
No, because it's not over the same base. Look, the sample here is true positive plus false negative, and here is false positive plus true negative. Okay, the denominator is different. So yeah, it's not a probability of both, no. Because the denominator is different in both cases. Okay, so basically we're going to calculate for different points. We will take a lean space between 0 and 1. We can take 0.01 as an interval and calculate the values of true positive rate and false positive rate for all of this. And this is going to make the curve. But what is most important is the area under the curve, which is the AUC. If you have an area close to 1, and I will see the interpretation. So the area under the curve summarizing the model ability to distinguish between classes. The model ability to distinguish between classes. And look, now we have a square 1 by 1. So the total area of this square is 1. Now, the area under the curve is the area now, if we make the sum of the area here, so this will represent the area under the curve. Okay, we can make an integration of this curve to find this area. And depending on the AUC, AUC is equal to 1. That's the perfect, I don't have any misclassification. I don't have any false positive rate. So I will have a straight line here and a straight line here. So this will represent 1 by 1, and I will have a perfect area under the curve. Now, if you have 0.5, okay, like this line here in red, it's like a random guess. It's 0.5 true positive and 0.5 false positive. So it's kind of random guess, uniformly distribute. And if the curve is smaller than this red line, it's even worse than a random guess. Okay, so it's usually a sign of a model issue. And anything above 0.5, of course, if it is much higher than 0.5, this tells us that the model is even better. Okay, so if you have 0.9, it means that the model ability is good to discriminate between the two different classes. The area by definition is the integration of the function f between the interval a and b. Well, here sum of histograms. It can be approximated by the sum of histograms. Yes, موجود in n functions that can calculate the area under the curve. So in Python there is already functions that can calculate this, but it is approximated by the sum of histograms. اللي تحت شوف area under the curve هي الاريا اللي تحت الخط الازرق. من هنا الى هنا شفت الان من هذه النقطه لهذه النقطه كل المساحه هذه تعتبر area under the curve تحسب. فهي باش تكون value between 0 and 1. Okay? Now, for example, for this case, or for the case of yesterday, it was 0.91. Okay, so it means a good discrimination model. على قدر ما تكون أكبر أقرب الواحد, it means that it provides much better performance. So this gives, usually in classification model, we care about F1 score, okay, because it is a combination between precision and recall, and we care about the AUC, which is obtained from the ROC curve, okay, the area under the ROC curve. So how to interpret the ROC curve? Of course, as already mentioned, higher AUC means better performance. It indicates that the model is good at distinguishing between positive and negative cases. Okay, for example, an AUC of 0.9 means that 90% of randomly chosen cases, the model ranks a positive instance higher than a negative one. So I will show you now an interactive visualization where you can change the value of the threshold and you will observe what's the point that corresponds to the ROC curve, because this ROC curve is actually constructed from multiple threshold points. And here I give you even the algorithm. Okay, so we can make a loop to calculate, to plot the ROC curve. Look how can we do it. So we create 100 threshold values, for example, from 0 to 1. And we will plot a point, okay, of the resulting false positive rate and true positive rate. So of course we can make predictions. We first make the predictions of the test data set, and it will provide as probability. So we're going to predict prob, okay? And we will check if the probability is greater than the threshold, we will assign class 1. And if the probability is smaller than the threshold, we will predict class 0. So you will see that the prediction will depend on the threshold. The same class can be 0 or 1 depending on the threshold. And then, based on the prediction that we got here, so now we have the predicted Y values, we can calculate the misclassification by calculating the true positive, the true negative, the false positive, and the false negative, simple statistics that we will calculate. Okay, yes?
Is there a logical way to interpret which threshold would be better based on the context?
Yes, now we want the threshold that will maximize the true positive and minimize the false positive. Okay, so in this case, we usually want to maximize the values, but you know, now this curve will give us an overall performance about the discrimination capabilities of that model regardless of the threshold value. Okay, and then we calculate TPR and FPR. So this will represent one point, XY coordinate, and then we will store it into a list. So we will have a list of points with XY coordinates, and then we plot this graph or this curve, and then we calculate the area under that curve. Yes?
Doctor, again, what is the threshold in this context?
The threshold is this one, because it provides us the highest true positive rate.
No, to plot it.
Yeah, this curve is plotted for 100 values.
Okay.
So we took values from 0 to 1, okay? And then 0, 0 point, I don't know, 001, 0.002, until we reach 1.
In the algorithm, it says, in step 2, it says for each threshold, you're comparing if the probability
Yes.
is greater than the threshold.
For each threshold, I will calculate the value of false positive rate and true positive rate.
Yes.
And for every threshold, I will plot a point. When making the interpolation between these points, I will have a curve. After getting this curve, we will use numerical methods to calculate the AUC, the area under the curve. It will give me a value between 0 and 1. If this value is very close to 1, it means I have a good discrimination model. If this value is very small, okay, it can reach random guess or even worse than the random guess. So basically from this value, you can assess whether your performance of that model is general enough and reliable enough to work in deployment. Okay? So it's better if you want to make a consistent classification, you should not base your values only on classification report, but it's better to assess and investigate the general performance of the model using the ROC curve and the AUC. Okay, so let's start from here. Yesterday we have already introduced this ROC curve. Now I understand the ROC curve, how it is calculated, but let's try to see this interactive demo. Look now, this is our data set. This is the decision boundary. And here we have what? This is a true This is true positive, and this is, what is false positive? This is false positive. This is false,
The truth of the-
Positive is down left.
yeah. So this is true negative, and this is false, false positive. It was positive, so misclassified, so it's false. Okay, this is false negative, and this is true positive.
Is this the same format you had in the slide?
Yes,
I think it was true positive top left, false positive.
because we had the yes on the top.
Okay.
Now this is the yes.
Yeah, so the format.
Okay, 1 is yes, and 0 is no. In the slides you have, it was reversed. Okay. So let's look now. This plot is for a threshold equal to 0.5. And now let's look at this one. Try to calculate this value. Look, true positive rate. This value is 0.92. You see? Try to follow here. And false positive rate, it's small. It's 0.1106. This is the precision, the accuracy. And the specificity. So all of these are performance threshold, performance metrics for 0.5 threshold. Okay, let's now try to change the threshold to 0.2. We'll make the, or 0.25. Look at the point now. What happened when I put 0.25?
false positive increased.
So the true positive just remained fine.
Increase the bit.
Okay, look, this is true positive, 100, still high. But I had more false, these are false positive. Look, 46 for positive. Let's look at 25. How many false positive we had? Look at this square, only 11 false positive. But when I changed to 0.25, you know why it was false positive? Because it will consider most of the cases as positive. 0.3 positive, 0.4 positive. So I will have many positive cases, okay? Which means that this threshold is not good to recall the positive cases. Look at the recall. I don't know if you have a recall here. The precision is smaller. Look, the false positive rate becomes very high. But the true positives still remain also high because everything will be classified as positive. Okay. So let's make high threshold now. Look. High threshold, it means many of the instances will be classified as 0, as false. So this is why we have a reduction of the true positive value. Now in this case, because we have kind of almost uniformly distributed points, so 0.5 was the best threshold. But in some cases, when the distribution is data is more complicated, some other threshold could be better. Okay, when the patterns are very complex. Now this pattern is not complex. The decision boundary is almost here in the middle, in this diagonal. And look now, we had an issue. We have reduced number of true positive, which we observed at this point. And we have an issue, okay, but also we have reduced the false positive because most of the classification will be considered as negative. Okay, so you can see the relation between them. Okay, and here I will show you how you can build. So this is the algorithm where you can build the ROC curve and also the AUC step by step. So it's basically the same algorithm. You take different thresholds from 0 to 100 values, and then for every threshold value, you will calculate the predicted probability, okay, and you will compare it to the threshold and you convert it to a prediction 0 and 1. We calculate our metrics, okay, for the true positive, true negative, false positives, and false negative. We calculate the rates, TPR and FPR, according to the equation. And finally, we will append them to a list. So we will have the XY coordinate, and you will use this XY coordinate to plot this curve. Look now, the AUC is 90%, so this represents a model with good discrimination capability. Is it clear?
Yes.
Okay. Now just to finish, in the last 5 minutes, we can do the same but for multiple class classification, okay, or multi-feature, multi-class classification. So here in the same way, we're going to generate data, but look at the pattern now. We have 3 classes, but here we have much more complex pattern, okay? It's difficult to make a separation using a boundary line like we did in the previous example. And you know that the logistic regression is basically a linear regression with a sigmoid function. So we will try to use a logistic regression and let's observe what will happen. Because logistic regression has a linear relationship trend or tendency. And this model basically doesn't look that can be captured by a linear pattern. We don't have a linear, we have a pattern, it's clear, it's circular. But here, if we try logistic regression by itself, even if it is multiple classes, you know, I can do the same for 2 classes and we can run logistic regression. It's not gonna work easily, okay? But look at this one now. And this is the distribution of data for the 3 different classes. Okay, so we will generate the multi-class data and then we will split it into training and testing data sets. And here we will train using 2 techniques. Both they use logistic regression. So one is called one versus rest classifier. It's going to take one class and classify it with the 2 other classes as one class. And it will do the same for each of the class. We'll fix one class and compare it with the others. That's one of the ways. So it still uses the basic linear regression, but with some tweaks. A more natural way is to use the softmax function. Softmax is like the sigmoid, but it will use like a function similar to the sigmoid, but for multiple classes. It supports multiple classes. So here we will use multi-class equal to multinomial, and this means that it will use the sigmoid function. Let's try both of them, using the fit for both of them, and printing the classification reports for the 2 models. What do you observe?
Very similar.
Is there any difference between the 2 techniques that we have used? No. What do you also observe?
Support نفس الشيء بالضبط.
Hmm?
السبورت نفس الشيء بالضبط.
Yeah, we have low performance for both models. Look, accuracy 40%, precision 39, recall 60% here, 47. So it doesn't seem to provide a good model. Why? Because the logistic regression basically it tries to make an assumption that there is a linear relationship between these models, and it's not the case. Okay, so this is the analysis. Both models have low performance. So another way, just show you quickly different techniques that we can do. Now it's because we are using a 2-dimensional space, so this model is not linear. But we can make data transformation. Okay, we can use polynomial features, convert the features to polynomial nature. So here we're going to use 3 improvement techniques. The first one is try to make regularization. Okay, regularization in this case is not going to work because we don't have an overfitting problem. We have a problem probably of underfitting, but it's one technique that we will use. We use regularization. Another one is to transform the features into polynomial features. So it's going to convert the features into a 2nd degree polynomial. Okay, so making this transformation, maybe we can transform the model into linear features that we can fit a logistic regression. I know probably you will not understand this transformation because this is something that we usually introduce in SVM, but this is what we call a kernel. So we can use the basic kernel, which is the feature themselves, and we can transform the feature. There are 2 types of transformation: polynomial transformation and also the RBF transformation. It's more complex, based on an exponential. It's based on an exponential function. So it's going to take it from one space. We apply a function, we transform it to another space to try to mimic the pattern here. So when we apply logistic regression, it looks like a linear transformation of this. So looks what happens here. If we train these models and make a classification report. So this is using regularization. Is there any improvement? No, because the data itself is still not linear. We didn't make any transformation on the data. Look now, with polynomial and RBF kernel, with SVM, its support vector machine is not. So this is logistic regression, applying a polynomial transformation on the features. Look, 99% of accuracy. Okay, it was able to capture the nonlinearity. Okay, because this circular pattern could be modeled by a linear or polynomial transformation, and then logistic regression. So it's like you go from a circular space to a linear space,
And then we
okay, and then you apply logistic regression. Okay, it's a space of PCA. It's transformation between different spaces, but here it's done in different way. And with RBF, we get also similar performance, applying the exponential function on the features, and then we can find decision boundaries. Look, the decision boundaries now are much clearer. And then you can find in some interpretation of the results. And look, this is the ROC curve for class 0, for class 1, and for class 2 by using the simple linear regression. And it's kind of random guess, as you already observed, because you have 30% for most of the classes. And you can see now we have ROC curve below the 0.5 line, okay, this diagonal. And we have observed the application in the classification report where most of the metrics were below 50%, okay, precision. Yes, any question?
Is it like an intersolid projection in circular space على linear?
Yes, it's like we are transforming a circular pattern into a linear pattern for the logistic regression to recognize.
نفسي مثلا sublime.
Yeah. Let me give you I have a video on YouTube on my channel, but I will give you also other videos that explain how to transform the data set from one space to another. So this will give you a better intuition about what is happening here. I need at least 1 or 2 lectures to explain these concepts, but now the focus is mostly on the classification problem. But I'll show you one video that will explain to you the transformation of the features from one space to another before applying any classification algorithm. This is something used in machine learning to improve the accuracy. Okay? Any question? Okay, thank you. This is the end of classification. So next week I will make 2 lectures on linear regression, polynomial regression in general, and how we interpret its results. There are different models. Some models are based on learning, some based on numerical computation for solving a linear regression problem. And then we'll have to the 2 last lecture, the review for the exam, inshallah.